All right, hello and welcome to a new week. We're going to finish up these slides today and then start some new ones as well. So let's go to where we ended. We stopped talking about stuff in Python, actually. It was a combination programming and non-programming lecture, and we talked about the goto function, which is quite nice. And then we talked about the essay and the evaluations too. Now, let's talk about some bad things, okay? And we'll continue with some bad things on the next set of slides. So, technology is very cool, but it can also do some weird things, and it's changing the way we think about the world. Okay, so let's talk about how we might go about evaluating technology, and also, if it's something worth controlling, how do we do it? Okay, so I'm going to try and answer this question. How can I cope with all the downsides of technology, because some do exist, and think critically about them? That is the goal of this class, right? So let's talk about something cool. You might have heard of Deepfake, okay? It is a very interesting application of machine learning. So it's when you use machine learning to swap faces in a video, which is really cool looking. So here is taking an actress, and I think everybody wants to put Nicolas Cage on everyone. I think they're turning it, the actress, into Nicolas Cage, which is nice. And then, of course, they're doing that down here, too. Yeah? So this is not a new thing, right? We had Photoshop. We've had it for a while, and it was very, very common for people to, like, change the face in a still image, but it took a whole lot of work to go and change a video, right? And so as a society, we trusted videos a whole lot more than images because of this. Okay? So we thought that videos, they're pretty good ways to prove that somebody was in a certain place at a certain time and that they did a certain thing. So for example, like security cameras. I don't think a jury would have any problem trusting a security camera footage. But now maybe it's not a good idea, right? Especially for high-profile cases. So Deepfake, this is a brand new thing. It's applying kind of Photoshop skills to video this time. So it's been used for fraud. Like, I'm sure you can watch, there's videos that have been made with Nicolas Cage talking, but it wasn't really Nicolas Cage, right? Hoaxes, it's easy to do that, to pretend that somebody is somebody else. And of course, when you need some more Nicolas Cage in your life, and don't we all? So this is just a weird new thing, relatively new, and it's giving us a reason to not trust videos anymore, which has some serious implications on our lives, I would think. Okay? So that's Deepfake. If you haven't heard of it, I really encourage you to look it up. You might go and look it up on Wikipedia, so let's talk about that now, too. So Wikipedia is a fun place. It is a wonderful repository of knowledge, and people are adding to it all the time. They make a new article. Here's a new article. I can write it about my cat, right? And they might let it stay up. That's nice, right? People are changing things all the time. And also the information that's on Wikipedia, it's really nice that it's editable by everyone, because something might happen and then Wikipedia, like, they have the scoop, right? It's there before anybody else puts it anywhere else. So yeah, that is the idea. So Wikipedia can be changed very quickly, and it's just always one page that you can keep coming back to. It is similar to news articles. They do change as more information gets released, but Wikipedia is like the ultimate news article in a sense, right? Let's say that. So news articles might change, but Wikipedia keeps changing forever and ever. So yeah, let's talk about this problem that apparently has a grammatical error. Anybody can modify a Wikipedia article. We've been saying that, right? I can write one about my cat. There he is with his whiskers and ears. And you could edit an existing article if you wanted to, about whoever you wanted to, like the Queen. Whatever you wanted, you could change, okay? You could add weird information, you could add incorrect information, and Wikipedia, thankfully, catches it a lot. They have automated detection of times when people are doing silly things, okay? But sometimes it can get past a human, okay? Sometimes it can get past the computer, sorry. And it takes a human to go and say, okay, that is not a real picture of the queen anymore. You changed it to a cat. How dare you? Okay, so that's how that works. And Wikipedia articles in themselves are not complete. Usually, there's always those citation needed blocks as well. So yeah, just keep in mind. I'm sure every English teacher has told you this already. Just keep in mind when you're using Wikipedia that anybody could write whatever they wanted to, and especially when there's no citations, it's really hard to trust. Okay? Does that mean you shouldn't use it? Again, let's pretend that I'm an English teacher, and I should say that as long as you visit the articles that are cited, there are citations, and at the very bottom it lists them, okay, this is a reputable source. If you go to those, it's probably fine to use, right? So this is the evaluating part. You should evaluate how you're using Wikipedia, okay? If you haven't already. So I guess I'm just going to throw a bunch of case studies at you in this lecture, in these slides, and then the next slides as well. Let's talk about some things. Okay, so this is a fun one from your book. So car crashes. It's very expensive to make sure that a car is going to crash and not kill people, right? You've seen those commercials where they got the wall, the giant wall, and they got the car, and it's about to, this is my best drawing of a car, and it's about to smash into the wall, and they have those little crash test dummies inside as well to make sure nothing bad happens to them. Well, that costs so much money to run a car crash test, to make sure the car is actually going to do the right thing. What if we just use software? What if this was a virtual car and a virtual wall? Wouldn't that be nice? Put that on a computer instead. Yeah, that would be beautiful, right? Yeah, the answer is of course yes, but the problem is you have to model how the car works. You have to model the physics of everything, and we're good at that. We know a lot about physics these days, of course, but we don't have enough processing power to model each individual atom of metal and every little particle that is making up a car, and all the concrete as well, of the wall. We can't physically handle that in a computer. Okay, there's not enough room. We don't know enough about physics to do that, right? So the simulations, they have to simplify how everything's going to work. Maybe they break the car into tiny little chunks, and they model those chunks accurately, but can you trust a little chunk is the question. So is this okay is the main question, and the answer is up to you. This is a question for the class. I would be asking you to debate on this if we were in person. So there are arguments for and against, of course. So one argument for would be yes, it's good because they're saving money. They can try a bunch of different car designs in the software, and the software is probably good enough, right? These little chunks probably are very close to what a car does, in theory. And once they're comfortable with the software simulations and the car's doing well, they can pick their best models, their best types of cars, their best designs, and perform a real crash test. They have enough money to make at least a couple cars, right? That's one argument for. It might make it safer in the long run. With all those simulations, right? Okay, that's an argument for. Sorry, the car's getting in the way. And an argument against now, though, is, well, what if the simulation had a little bit of an issue or it wasn't accurate? So maybe if they just did a bunch of real tests for real car designs physically, in person, they would have come up with a safer design. So that's a for and against argument, and I'd like to hear yours if we were in class. So that is car crash tests. Let's talk about something a little less serious. Let's talk about your phone. Okay, so Google makers of Android, of course, they can delete an app from your phone. They have that power. So the idea was they were supposed to be able to do that because like some weird stuff can get on the store, and an application might be malicious, and they might notice that after the fact, after it's already up and people have downloaded it. So it would be nice if they could just delete it from your phone to make sure that you don't use it, because that would have been a bad app to open, right? And the question is, should they be allowed to do this? Like, is that infringing on your rights to have software on your phone? Because maybe it wasn't a malicious application, but it was just an application Google didn't like. What's stopping them, right? This is technically a fallacy. It's a slippery slope fallacy, but let's think about it, right? It's possible. If they have this power, they could use it wrongly, right? Apple is not immune from this as well. They have done it before also. So back in the day, recently, they took down Fortnite for breaking their App Store rules, if you remember that in the news a few months ago. That is unfortunate. And the reason that they did that is because Apple needs a cut of all the purchases. They require that in the developer agreement that they have everybody sign who wants to put their app on the App Store. So they want a cut of all of your all the money that you make. And Fortnite was not about that, because why would they want to give Apple that much money? Because they were making so much money, right? So they wanted a cool deal for themselves, and there are arguments for and against this practice, I think you can imagine. So that's the idea. Yeah, Apple thought, like, these are our rules, you didn't follow them, I'm going to remove you. Okay? So, and they removed the software from the App Store. They removed Fortnite from the App Store. But then they didn't take it away from anybody's phone who has already downloaded it. Okay, so there are many different sides of this argument and different levels of problems with phones and apps and app stores. As a final note, let's talk about Amazon, who makes the Kindle, right? Which is technically sometimes an Android device, depending on which one. So back in the day, they accidentally removed copies of 1984 from some customers' Kindles, which is a wonderful example of irony, I think. Okay, so I guess this is just another example. This has happened. It's been done. Do you agree with it? That's all I want to do. I want to prime your mind to get ready for a future essay or something like that. Okay, I'm giving you a bunch of little examples. Okay, let's talk about computers. Let's talk about Windows. So it's possible to make a piece of software this time, not hardware, software, and force a user to update that software if they want to use it anymore. Like, they don't have a choice. You are forced to upgrade. We're going to do it for you. So if you remember this story, Windows 8 used to be a thing, right? It used to be out and popular. And then Windows 10 came out. And Microsoft thought that Windows 10 was so much better. And so they automatically started updating everyone's Windows 8 installation to Windows 10. Okay? And that is a very, very interesting thing. Should that be allowed, is the question. So I guess the real question is, do you have control over what's done to your computer? And I think you would try and argue for yes, usually, right? Who knows better than you? Maybe that's not true for like an older person who doesn't really know computers very well. That was probably a good thing that they got upgraded to a safe version of Windows that was going to be looked after for a bit longer. So there's so many different sides to this coin, of course, as usual. What do you think, I guess? So I've tried to come up with one argument for and one argument against again. So an argument for doing this kind of thing, for actually forcing people to update their software, is that, okay, the older software, it usually has holes in it, right? People are updating things not to, well, sometimes to add more features, but also to like clean up all the holes that used to be in that software, right? It's nice to have that automatically done for you, especially like for your parents or your grandparents who may not be so good with a computer, right? and then against, then as a consumer, you're kind of forced to give up your control, right? You have no control over the software that you just probably spent a good deal of money for, right? Which is no fun. So maybe you should have control. So again, this is a question for the group. What do you think, right? Do you agree with this? Maybe, I guess you can talk with your money and just not buy Windows ever again, if you would prefer. And then finally, something very, very important about all this technology that has good sides and bad sides and needs to be controlled. Are we controlling it the right way? Are we giving technology to the right people? Is everyone getting enough access? So I'm sure you've seen this picture before. It's the classic one that explains what equity means. Let's talk about it. Equity with respect to technology. So plenty of low-income households, they don't have the computers, they don't have the devices, they don't have the internet connections, or the people connections that could help improve their lives. So we're all working remote right now, and it is a luxury for me as a teacher to be able to do this, right? I'm in a very good position, and I acknowledge that, okay? A lot of people don't have it this good. So if, for example, you don't have a phone or an email address, you can't get an interview for a job that you could have, and it would make your life better, potentially. Okay, so that is something we need to think about as a society, right? So, and of course, especially during this pandemic, it's a bad thing to be without technology in a lot of cases. So let's change the focus to you as a student. Like, I'm sure a lot of some of your classes have required you to use like Proctorio or something. And maybe your computer doesn't have a webcam, or your internet connection sucks. You can't take that proctored test, can you? And so you have to either drop the class or talk to this teacher, and then it's always not fun to talk to a teacher sometimes. I hope that you're willing to talk to me at least, but I know it's not the easiest thing. So it kind of ruins your experience, right? And that's no fun. At least here we try and like give out laptops and little wireless routers, but a lot of people don't have it that good, right? And we have to acknowledge that. And then finally, before we go, something that I just want to bring up is there's a bit of a gap in terms of technology and race as well. So a lot of programs, when they're written in their like the fancy offices in California, they're tested on white people, right? That's unfortunate. They're tested on the majority of people that they could find, and often it's just a bunch of white people. So sometimes if you get this fancy technology, it's not even going to work for you if you're not white, which is really unfortunate. Like, for example, maybe you're making a machine learning program and you're testing like facial recognition for like a password. You use your face as a password or something. If you train your machine learning tool on just a bunch of white people, it's never going to be able to detect anyone else. Okay? That is a huge, huge issue, and it's something that needs to be dealt with. So I just want to get this in your minds because you are the future programmers, right? I hope that you, when you're a future boss at a tech company, you make your employee base very diverse, and you make sure to give back. And with that, we are done with these slides, and we're now ready for some new ones. Okay, this one's called Computer Risks and Bugs. So more bad news, sorry. Let's get started. So errors, failures, and risks. Oh my. What else has gone wrong, right? I'm going to try and answer how in the world can we manage to still use computers and trust them when they cause so many problems? I'm sure if you've started the essay, you will have not been happy when you read that article, right? Why do we trust computers so much if they can sometimes mess up big time? Okay, let's talk about Ariane 5. So this is a rocket. Well, I'm trying to Oh, it's not happy about me drawing. Aha. This is a rocket, in case you were wondering. It was called the Ariane 5. Obviously, it was the fifth in a long line of Arianes, and it was made by the ESA, so not NASA, but ESA, which is, I think, European Space Agency. So it was made by our European brothers and sisters, and the first time they tried to launch the Ariane 5, it didn't work out so well. Okay, so what it did was, it was getting up in the air, and it self-destructed. Oh no. And this was back in 96. Okay, so a nice Independence Day fireworks parade if you're in America, but not, unfortunately they weren't. They were in Europe, right? So this was only 37 seconds into flight. So can you think, they spent so much money, $370 million, and they lost it immediately. And they had some like satellites on board. This was an unmanned rocket, by the way. Nobody got hurt, but like all the satellites that they were trying to launch into orbit, they of course got blown up, which is no fun. So they lost a ton of money, and everyone was not confident in the European Space Agency anymore for a time. So what was wrong? What happened? Why did this happen? And unfortunately, as a computer scientist, I say unfortunately, it was because of a software bug. Let's make sure this is all still recording. Yes. A software bug blew up a rocket. Oh no. Why? What in the world? What happened? Okay, so let me tell you about the problem. You're now expert programmers, and I can tell you exactly what was going wrong. So I'm going to try and break down this phrase right here. They tried to put a 64-bit floating point number, float. They put a float, so a number with decimals, like 3.14, right? They tried to put it into a 16-bit integer, okay, which can only hold whole numbers. So like it can hold 3 and then 4. There's nothing in between for an int. And 64-bit and 16-bit tell you how precise the numbers were. So a 64-bit number has 64 ones and zeros, right? And it can hold a lot more numbers than a 16-bit number. So 64 binary digits, right? That's quite a lot. Versus, like, relatively, 16 bits. There is no contest. You can put so many more numbers, you can fit so many more in a 64-bit number. Okay? Not to mention, floating point numbers could hold decimal places that integers cannot. I think that was beside the point here, though. So, you know all these words, and I think I just explained what they mean together. Okay? Hopefully that makes sense now. So they were trying to take a big number and shove it into 16 bits from 64. Okay, hopefully that makes sense. And the problem is, when you have so few bits, let's pretend we only have 4 bits to work with, once you get like high up in the numbers, like you have 1110, and then you add 1, you get 1111, and then you try to add 1 to that. Let's pretend we just have 4 bits. Suddenly you're carrying all over the place. This is how you add in binary, and you don't have room for this digit. You only have 4 bits. Uh-oh. This is called overflowing. Okay, you didn't have enough space in your number representation to store the new number. Okay, so there wasn't enough room to store this converted number from the rocket, and this was a very important number. Okay, it was storing how it was horizontal velocity. So it was storing like how fast it was moving relative to the ground, not straight up. So like here is my best drawing of Europe. There's Italy, there's Russia, here's the UK. They were storing horizontal velocity, which is like velocity along the ground. Okay, that is a number. And if your rocket doesn't shoot straight up, it's going to have some kind of horizontal velocity, because maybe it's going like, there's the rocket. Maybe it's going out a little bit to the right or something. Okay, so that's the idea. And so they were trying to store that number. They're trying to convert it down to a 16-bit integer, and it was originally saved in a 64-bit floating point number. And So what went wrong? So what they did was, this is Ariane 5, they had an Ariane 4, they reused the code from Ariane 4, okay? Which is a nice time-saving thing a lot of the time. It's like, okay, yeah, we've already implemented this code once, let's just reuse it. It obviously worked on the Ariane 4. But back then, they never thought that this number that stored horizontal velocity, they never thought it would get so big, because apparently the Ariane 4 was a lot slower than the Ariane 5, okay? Or maybe they launched it straight up or something. That's the idea. Okay, so all of this, it just created a perfect storm, and this rocket didn't get to this place in my drawing. It blew up very quickly. Okay, so, and that was a huge, huge software bug that could probably be fixed with a few lines of code. Okay, so that is very unfortunate. Why should we trust anything to have to do with software? Okay, that's no fun. Okay, another fun example, voting systems. So this is relevant, right? This is another example from the book. So back in the day, there were some electronic voting systems, and they crashed on election day. Okay, so voters who wanted to vote, they were unable to. Maybe they let them like sign a little paper one, hopefully, or maybe they just made them drive somewhere else. But I think you can imagine that some people didn't vote when they really wanted to. Okay, so that's a problem with a voting system. That has happened before. Additionally, votes have been lost when a voting system had been made electronic. Okay, so maybe too many people had used the voting system that day, or it couldn't connect to the internet and like shove off its results to whoever needed them. It had to store them in memory for a little while, and that memory got to be full. Okay, so 4,000 votes were lost because of that, and nobody knew about it. Okay, and I'm sure they didn't even know. Like it was very hard to find this out, I'm sure, right? So hopefully they tracked down those 4,000 people and had them vote again, which is really, really unfortunate, right? So that's a second problem. How about a third? So in one Texas county, it's unfortunate that it was Texas, a programming error generated 100,000 extra votes. That is horrible. That is third world country voter manipulation bad. Okay, that is very unfortunate. And that happened in Texas. Insane. Okay, and then finally, the worst probably is, well, depending on how you feel, the worst. This is also a very bad one. Another bug in code, just a programming error. It caused some candidates to receive votes that were really cast for somebody else, right? So you voted one way, it made you vote the other way. That's horrible. So this is all just a bunch of bad news, I guess, but we're trying to solve this problem. Like, we want to trust technology. My livelihood depends on technology, right? I'm a computer science instructor. Surely we want it to stay around, right? How do we keep it around and not hate it, is the question. So I think we've discovered with enough examples that it's very hard to write software that works, that's correct, that's safe, that can't be tampered with. That's the idea. And some people have done it right? So Estonia, for example, all of their citizens, they vote online. They don't have to go anywhere. They can vote online, and they trust that, and it's been shown to work. So why can't we have that here, I guess is the question. How can we make voting safe? How can we make software safe? Because surely they've done it in other places. Let's do it here. I'm just trying to get that into your mind. We're going to talk about a way to make software correct and safe and trust it in just a few slides, if not today, then next week. Now it's time for the topic of your essay. Let's talk about Therac 25. Okay, so another horrible, horrible accident, or set of accidents, happened because of this machine. Okay, so the Therac 25, if you haven't read about it yet, it was a radiation therapy machine. So people with cancer would come to get their cancer treated by this machine. It would target the cancerous cells and hopefully help to kill them off, right? And so this was Therac 25. Again, this is a number that is not 1, so there were other Therac machines back in the day. This is again the problem, or so we will see. And they were first made in 1982, okay? So relatively far off, like before I was born even, probably before you were born too. And the first documented accident, it was 3 years later. So either things weren't happening, or they were and they just weren't being caught. But it took 3 years for them to discover this horrible, horrible problem with this machine. Okay, so can you imagine how many people they treated in those 3 years that may have been accidentally given more cancer because of the amounts of radiation that were transferred into them? It was horrible. So I guess I'm kind of jumping the gun if you haven't read the article yet, but here was the problem. So the issue was, it was not just a code error, but the code didn't help, right? It was really a design and a code error. So errors in both of those, they ended up giving people up to 100 times the amount of radiation that they were supposed to get for their treatment, which is horrible, right? That's the worst thing. You're trying to come get your cancer treated and they give you more cancer, right? That's ridiculous. So the issue is, I guess the code was originally wrong. That's the idea. And the old Therac machines, whatever their numbers were, I don't remember, the previous versions of that same machine, they had hardware systems to block the radiation from ever getting so high that it hurt people. Like there was a hardware little piece of lead or something that would block the little radiation beam whenever it wasn't in use, was the idea. And unfortunately, they got rid of that thing, that blocker, in the Therac 25. They thought the software was good enough, and so they reused it and got rid of this, which I'm sure did not help a lot of people out. Okay? So this is a horrible, horrible problem and a failure, and it's taught to every computer scientist. Okay? So now you're knowing it. Now you're learning about it. Okay. So that was disgusting, horrible. Let's talk about blame for a second, because this is extra bad. Okay, people are dying. Okay, at least in this case, people are dying. How do you reconcile this, right? How do you assign blame to software when people got hurt because of it? Okay, is it the programmer's fault? The idea is, again, grammatical error, sure. Software wasn't made by one person, usually. Like, I'm including the Therac 25. I'm sure there was a huge group of people who were working on this, and they all signed off on it, right? And that is a problem for assigning blame. It's kind of impossible because of that. So usually a lot of people in their software development teams, first of all, they're on a team, and they work on a little piece just for themselves. Okay, they have their little chunk of code that they touch, and they own it, right? Nobody else gets to touch that. It's theirs. And maybe other people look at it, make sure it's going to fit into the larger piece of a bunch of little chunks of code written by other people. They all come together to make one big coherent piece of software, right? A lot of the time, when you're working on your little chunk, you don't know the big picture. You don't understand the full system because it's so complex, right? That is true a whole lot of the time, okay? For any large piece of software, nobody's going to understand it fully. That's just the unfortunate fact about it. Okay, so that's one thing. It's hard to assign blame because of that. And also, errors are so common, right? You've written enough code now. I've forced you to write enough code in this class for you to know how hard it is to do it right the first time, okay? It's so easy to make a program that does something just subtly wrong, or completely wrong, right? Subtly wrong too. So here is where I give you the solution, okay? This is the solution. Maybe I should put that in bold. I've capitalized the two words for extra effect. Testing, software testing, and software verification are our only hope, okay? That is going to be how we get out of this hole that we dug ourselves into with code that's easy to get wrong, okay? And a bunch of people on teams working together, but not really understanding the full picture, okay? I'm going to talk to you about what testing is and what verification is. They are slightly different things, okay? In computer science, they're different. In English, you think that they're like synonyms for each other, but they are not, okay? They're not in computer science, at least, but they are in English. Okay, so the easiest way to test code is to test it, okay? So what does that mean is the question, and that is what I'm about to teach to you. So testing is when you write your code, right? Let's pretend that your code is this box. And your code takes inputs. It's like, okay, input 42, and then your code gives back 13. And then you input 27, and it gives back 88, right? That's how your code works. It takes inputs, and it gives you back outputs, right? In some form. Maybe this is like a game, and you press up, and the player goes forward, right? So you can think of any piece of code as just a black box that takes inputs and gives output. Okay, that's all code is at the end of the day. And testing is for you to try a few inputs and look at those outputs, okay? So if you say, I'm going to try 42, I'm going to make sure, because I know the answer, I can run the code in my mind, I know what it's supposed to do because I implemented it, I'm going to make sure I got back 13, yeah? That's the case. That's the idea. So example test, I should say. So here's an example test. So I'm going to put this into my box. So try input 42 and make sure, confirm that we got the output 13. That's all a test is. It's like, all right, I'm going to give this value as input, and I'm going to get this value as output, hopefully. I'm going to make sure that it gave me that. Okay? So as a programmer, you have to write these, and they are finite a lot of the time. So as with any finite thing, it's not going to catch everything. It's not going to catch every problem, because there's like an infinite number of numbers, right? So it's not going to catch every problem unless you have some really good tests, which it is possible to do. But the idea is you're going to make not just one of these, but a ton, right? These are like, these are your stacks. Like here's a big stack of code. See, all these little tests. It's a big stack of cards, right? That's what you want. That's what testing is. But unfortunately, as you will discover if you continue into computer science, everyone hates writing tests for some reason. It's like, it's not the cool part of your code, right? It's like, okay, I've already written this thing. Yeah, let's just make sure it does this little thing a few times. That's not fun for anyone. But it's very important to do. Okay? So that is testing. Now, let me give you an example, and that'll be it for today. We're going to write a program, and then we're going to write a test for that program. So let's see if I can make this bigger so that we can read it all. Sorry, it's so many words, but it's very important. Very important words. So let's try this. It'll work for me. So here's the idea. Let's pretend we're back in Scratch, because we love Scratch, right? Let's pretend that we're going to make a multiply the numbers from 1 to n block. So here's, and you can give a number. You can give 42, you can give whatever you want. Okay, so let's pretend it was just 4 or something. Something easy. And maybe the goal of this block is to like print out the answer, right? So let's pretend that we've made this, and we can use it now. Okay, how would we first program it? Here's the idea. You start out your counter, or your product. You'll have a product variable. You'll start at 1, and then you'll have your n variable that you can have, and perhaps change it, like n starts at 4, and you'll just keep multiplying n into product. So 4 times 1 is 4, then change n to be 3, then multiply it into product again. 3 times 4 is 12, then make n 2, multiply it into product. 12 times 2 is 24, then make n 1, multiply it into n, or technically you could stop there. 1 times 24 is still 24, make n 1 less, n is now 0, so we're done. That is essentially the code that you would write, and then you give back the answer in product. It's 24. Okay, now that is the idea. That is our implementation. How do we trust it? Okay, let's write some tests. So a good idea is to test what's called the corner cases, right? Places where things are almost correct or almost not correct, okay? I should say. Almost correct or almost not correct. And I'll show you what that means in a second. Okay, so that is a corner case. So for example, if n was, I don't know, 1, that would be a good corner case. Make sure that when you give 1 as the input, you get back 1 as the output, because 1 is the last number that's going to multiply in to the product variable, right? Or so that's how we're going to pretend that we implemented this. The second you give n being 0, then that's another corner case, because it's right off the edge of what your code should do. And it's up to you as the programmer to figure out what to do here. So you have to pick a case for this. And you can see how the code is kind of leading you to this test. Because like, okay, we did some special stuff once n was 0. Like we stopped our work. Maybe we should get back 1, but no, that's not the answer. What do you do? What do you do in that case? Okay, so those are the corner cases. They're where your code is still kind of correct, but it's about to not be. Like if your input was only a little bit different, or your code was, sorry, the first one was this one, and then 0 was this one. It's like almost correct. If I gave 1, it would actually give me back a real answer, because multiplying the numbers from 1 to 1 still makes sense. So those are your corner cases. So here are some close ones. 2, 1, and 0. Those are where your program should do different things, right? So you can also think of it that way, where your program is about to do something different if the input had changed. Okay? That's what it means to do a corner case, and so those are a bunch of good tests to have. Okay? Those are probably the best tests to have, because usually you can think of the normal case in your head. Okay, then you test the totally incorrect cases. Like, okay, the user gave us negative 42. We're supposed to multiply the numbers from 1 to negative 42 now. User, excuse me. So again, you have to figure out in your program, what should you be giving back? Should you be saying printing an error or something? And maybe if you do that, you'll have to test that you printed the error, right? So those are also very good test cases. And then finally, you test a few normal numbers to check the general case. Like, okay, make sure n equals 5. Make sure n equals 4 works. N equals 8. Okay? Try all these things and compare what you got. That's the idea. This is what you got. Right? This is the input. Oh, sorry. And what you got was the output. And you make sure that it matches what you expected. Okay? You give an input, you get an output. So compare what you got as output with what you expected to get as output. Okay? That is what it means to write a test. Okay? So I encourage you to code this up, code this particular block up in Scratch, and try to think of a bunch of different test cases and notice why these are corner cases, why they're different, and why you would care about knowing what they do. Okay? So the best practice is to practice. Okay, so I think that is where I want to leave us. We have been through a lot today. I know, I'm sorry. So we've talked about bad things. And do we have some good things on the horizon? Probably not for this set of slides, But as usual in the programming lecture, we'll have some fun. Okay, so that's where I want to leave us now. So I will see you later in the programming lecture.